Oh, thank you so much for confirming that. Okay, so today the focus is going to be on analysis of variance. And of course, this is actually going to be seen in chapter 14 of the recommended textbook that we're using in this class. Okay, so before I go into the analysis of variance, I think I'm actually going to have a recap on what we've done before we get here. We started, the focus last week was to compare two groups. Okay, we compare population parameter in two groups. Okay, and the population parameter that we talk about could actually be what I call, proportion or means. Okay, and uh, when we compare the population parameter in two groups, of course we try to construct what I call confidence interval, and we also conduct hypothesis testing, and of course I give assumptions under which we can actually do that. But what of in a situation where we basically want to compare more than two groups? I'm going to say that again. Situation where we want to compare more than two groups, the technique that we used last week is not going to work. Okay, it's not going to work appropriately. Okay, and therefore, if we want to compare, okay, the population parameter, particularly comparing means in more than two groups, we're basically going to use what I call the analysis of variance. Okay, so I'm going to actually start with this, comparing more than two groups. Okay, for instance, we got a research question, and let's read the scenario now. What is the most effective method for treating anorexia? Okay, 72 anorexic teenage girls were randomly assigned to one of three treatments. Okay, the first treatment group received the cognitive behavioral therapy, in which girls are taught to identify the thinking that triggers their eating disorder and to replace it with the other thoughts meant to prevent this behavior. Now, the second treatment group attended family therapy, and the third group served as a control group and did not receive any therapy. Each girl was weighed before a treatment began and weighed again upon the completion of the treatment. Now, the data set for that can be found on this link. And let me just tell you this. We got three groups here. Okay. The very first group is those who actually complete cognitive behavioral therapy. And the second group is those who complete the family therapy. The third group is basically going to be a control group. They don't receive any treatment at all. And because of the fact that we actually are focusing on more than two groups here, we're going to use the idea of analysis of variance. The idea behind it is just like want to compare means in more than two population. The mean we want to compare here is actually the mean weight gain. Okay, what does it mean weight gain? After completing cognitive behavioral therapy, is it the same thing as the mean weight gain after completing the family therapy, or the same as the mean weight gain with no treatment at all? Now, like I said, because we got three groups, we're basically going to use analysis of variance. I remember when I was in school, I remember the question I asked my professor then, when the professor was teaching us this. I said, why is it called analysis of variance? Why not analysis of means? Because here we're comparing means in three populations. Why not analysis of means? Why is it called analysis of variance instead of calling it analysis of means, despite the fact that we're comparing means? Okay, but the kind of response I got? The kind of response I got is just like, even though we're comparing means, we're basically going to be analyzing the variations. I'm going to say that again. What actually make the mean to be mean in the first place? Why we are calculating the mean in the first place? Because there's a variation. If there's no variation at all, the idea of the mean is not going to come into reality. We don't need mean if there's no variation. And that is the reason the best way to compare means is basically to analyze the variance, which is the variation we're talking about. Can you all confirm again if you're still hearing me clearly? Is everyone still hearing me clearly? Is everyone still hearing me clearly? I just want to be sure.
Yes.
Okay, thank you so much. Just like what we do in the regular class, you can ask me question, you can uh, if you want to ask question, you can raise your hand or you talk by asking me question. Okay. Now, are any of the treatment better or worse than the others? That is, we basically want to figure out if a significant differences exist among the means. You can say I use a mu1, mu2, and mu3 to denote the mean weight gain. Okay, I just wanted to see that. Okay, so what is the goal in analysis of variance? Okay, the goal in analysis of variance is to compare the means of more than two groups. I just wanted to take note of that. When you actually want to compare means in more than two groups, what we're going to use is the analysis of variance. And of course, this technique was actually developed by Ronald Fisher. Okay. Okay. Now, why not just now? I want to say this. You know, why is it that we cannot just use the approach that we used last week? Okay, if I have three groups, what prevents us from just having a pairwise t-test, like compare, compare two groups at a time with the t-test that we did last week? Why is it that we cannot do that? Why do we have to go for analysis of variance? I'm going to tell you now. Every of those tests that we mentioned last week is actually characterized by type 1 error. When you want to conduct hypothesis, we always put forward what we call the level of significance alpha, which can be 5%, that actually represent type 1 error. Okay, which means we're trying to tell the world the probability of misleading the world is 5 out of 100. Or we're trying to say the probability of rejecting the non-hypothesis when the non-hypothesis is true. That is that 5%. But let me tell you this. In a situation, instead of you to use analysis of variance, and you decide to use a t-test, comparing two groups at a time, then the implication of that is that the type 1 error rate will increase. Because the type 1 error rate depends on the numbers of tests. When the numbers of tests increases, the type 1 error rate is actually going to go up. Okay, it's actually going to go up. Now, I'm going to give you an example now. If I have three groups, okay, the possible numbers of POS tests they can actually they can actually get with three groups, or is using this formula. Here, if G represent the numbers of means, in the example, we're having three means, right? If I basically want to know the number of of t-tests that I'm actually going to conduct, if I want to compare two groups, it's basically going to be 3 combination 2, right? Okay, 3 combination 2. So which is going to be 3 into 3 minus 1, right? Divided by 2. Look at the formula here. And of course, what am I going to have? I'm actually going to get 3. It means the numbers of tests, the numbers of t-tests that I'm actually going to conduct on 2 groups at a time will be 3. And if it is 3, let me tell you, okay, this is going to be the type 1 error rate in that situation. 1 minus alpha raised to power n. Okay, where n equal to 3. If you plug in 3 here, and if you're using the level of significance alpha, we should go with 0.05. Okay, this is going to go up. Okay, the type 1 error rate is going to go up. For instance, if n equal to 2, if you're using 5%, the type 1 error is going to increase to 10%. And that's not good at all. And that is the reason why we don't want to conduct a t-test comparing 2 groups at a time for a situation where we have more than 2 groups. And that justifies the essence of using analysis of variance, because as proved by Ronald Fisher in 1925, the analysis of variance will restrict the alpha, the level of significance around that is 0.05. If we're using the 0.05, or whatever the level of significance we're using, okay, using the analysis of variance for comparing means more than 2 groups, of course, the family error, the family-wise error rate that I call the type 1 error rate will not increase. Okay, so this is to justify the use of analysis of variance when you are comparing, means in more than 2 groups. I think I just justified to you now the reason why we cannot use the conventional t-test or, comparing 2 groups at a time within the 3 groups, because, for 3 groups now, the possible numbers of t-tests that you're actually going to conduct is going to be 3. And of course, the alpha, when alpha equal to 0.05, it is only 0.05 for one test. The moment you go to more than one test, that particular level of significance is going to go up. And when it go up, when the type 1 error increase, oh my God, we can't trust that research. Okay, I think I just justified that to you. Is there any question at this time? Okay, if you really go with my explanation now, I need you to say yes, or you comment yes. I'm going to say that again. If you understand what I just explained now, I need you to say yes, or you comment yes. And if you don't understand, please ask me question. I only saw one response now. I saw one response now. I want to make sure I carry everybody along, okay? If you want me to re-explain this, I also need you to say that. If you really understand, okay, I think I've seen some people, they say they understand. Okay, I'm going to move on. Now, we have different types of analysis of variance. Okay, we're going to start with one-way analysis of variance. What do we mean by that? In the one-way analysis of variance, we're actually focusing on one factor, one categorical factor. But only that this categorical factor has 3 levels. In the treatment that we just talked about, okay, you have 3 levels of that. Okay, the family therapy, the cognitive therapy that you mentioned, and the placebo, that is just one factor, except that the factor has 3 levels. Okay, with that, we're actually going to use one-way analysis of variance. The one-way analysis of variance is actually telling us we have one categorical factor with levels. Now, I want to familiarize you with the notations that we have here. In the notation, G represent the numbers of groups we're comparing. If like in that example, G equal to 3. The N is the sample size of the height group. It's just like within a particular group, how many samples do we have? Like how many participants do we have in a particular group? And that's why you see NI. And the big N here is actually the overall population size. Overall sample size, because that's going to be overall sample size where we are adding the subsample, the number of participants in each group when you add them up, and that would be the overall sample size. And of course, the Y bar, the YI bar is the sample mean of the ith group. Don't forget, from each group, we're basically going to find the mean of each group. Okay. And the Y bar here is the overall sample mean. When I say overall sample mean, when I find the mean of all the observations, when I pull all the participants in all groups together and I decide to find the mean, that will be the overall sample mean, which is the sample mean of all the observations. And I'm also going to have SI. The SI now going to be the sample standard deviation of the ith group, which means in each group, I'm actually going to find a sample standard deviation of each of that, just like the same way I calculate the sample mean of the ith group. Okay, and of course, the one-way analysis of variance compare population means, okay, among G different groups. Okay, take note of that. Okay, now let me tell you this. If you actually want to test, conduct an hypothesis testing, okay, the hypothesis formulation that you're actually going to have, okay, is what I'm actually showcasing now. When you take a look at this guy now, that's going to be the H naught, right? Where I'm actually going to have mu1 equal to mu2 equal to mu3 up to mu-g, depending on the numbers of groups I actually want to compare. If I have 5 groups, I'm actually going to write mu1 equal to mu2 equal to mu3 equal to mu4 equal to mu5. Depending on the numbers of groups I'm actually want to compare, that is the way I'm going to put it. Now, the alternative is basically going to be at least 2 of the population means are unequal. This is the way you're going to put it all the time. Okay. Now, what do we actually want to test? We want to test H naught. The H naught is more or less saying that, the response is the same across group. Okay, the mean response is the same across group. That's all it means. That's exactly what we want to test. Okay. Okay, now, whenever we're dealing with the one-way analysis of variance, we got 2 types of variation. I told you the other time in class, we find ourselves in a world where there's variation. Okay. We live in a stochastic environment. We live in a probability space. And of course, and that is the reason why we actually need to analyze variation. Okay, there are 2 types of variations as far as this is concerned. We have variation between groups and variation within groups. Now, what do I mean by variation between groups? When you are comparing group more than 2, we want to believe that we actually call them groups because we realize that there's going to be variation between them. That's why we call them groups. If I used to tell people that if we are the same, like we're actually going to be in the one class. The fact that we are in more than one class actually tell us the existence of variation. Okay, so variation between groups is just that. Okay, when I go into group 1, I find the mean. Group 2, I find the mean. Group 3, I find the mean. Now I actually want to know how much do these means differ. The mean of what? The mean from different groups. That's what I mean. How do they differ? That's what I mean by variation between groups. But when I talk about variation within groups, okay, the variation within groups, I'm actually going to be focusing on the individuals in that particular group. Of course, in a particular group, that we actually claim that we are more or less the same in the group, variation still exists. Don't forget, even variation still exists within the same group of individuals. And the question now is, how much variability is there within each separate group? That is exactly what we mean. So in analysis of variance, we focus on variation between groups and the variation within groups. Okay, I want you to take note of that. Okay, now the next thing I actually want to talk about now, the research question, if our goal is actually to compare the means of several populations. Okay, why are we doing analysis of variance? I think I mentioned this the other time. You know what, this is the same question I asked my professor when I was in college some years back, and I said, you are comparing means, why not calling it analysis of means? Why are you calling it analysis of variance? It's actually called analysis of variance because in the first place, we can never have, the reason why we actually need to compute mean is because of variation. If there's no variation at all, we don't talk about mean. And of course, in comparing means of groups, then the focus should be on the analysis of the variation that occur. And you know what? The variation can occur within within group, and variation can also occur across. And let me tell you this, in class, part of the preliminary investigation in statistical analysis is for us to first have a descriptive statistics where we exploit our data set. How do we do that? We actually going to construct, like in the analysis of variance. Don't forget the other time I told you, if you want to have a comparative analysis, because don't forget, we basically want to compare means in more than in more than two population, we can actually start with what I call box plot. Okay, if you take a look at this now, I got group 1, group 2, group 3. The box plot here, we actually send an information across that, okay, looking at this now, it's looking as if the means are not the same. But the box plot will only give us the idea of what to expect. But even if it's showing a difference, the only way to investigate whether the difference is significant is to conduct analysis of variance tests. I'm going to say that again. The only way to test whether the difference that exists is not due to chance. Because let me tell you this, if you take a look at the hypothesis I stated here, the non-hypothesis here is basically saying, right, there is no significant difference. Why the alternative is saying there is a significant difference. Whether you are talking about the non-hypothesis or you're talking about the alternative, difference exists. I told you the other time, we find ourselves in a world where there's a lot of variation, and of course, and that is what makes the world to be probabilistic in nature. So the difference exists in the two hypotheses, only that in the alternative, the difference that exists is very much pronounced. It is significant. In the non-hypothesis, we are also saying there's a difference, but the difference is not significant. So which means the difference in the non-hypothesis, the difference in the show can be attributed to chance. Okay. Okay, I think I just explained this now. And of course, this is the observation of what we notice in the part 1 and the part 2. Okay, if you take a look at this guy here, okay, the variation between sample mean is small compared to the variability within groups. Okay, if you take a look at what you see here, and of course in part 2, variability between sample mean is large, comparison to variability within groups. So which means when you take a look at this, even though different exists, but it's not very much pronounced. But when you take a look at this guy here, oh my God, there's a huge difference between the groups here. Take a look at that. A huge difference. Okay. Like I said, the box plot is basically going to pass across, something maybe is actually going to give you something to think about, like, but it is, necessary, but not sufficient. Get what I mean? Okay. Now, and that was why I have this conclusion. Differences in means in plot 1 are probably due to chance, whereas plot 2, the differences are probably due to true difference among groups and not to chance. Okay. So which means now when you take a look at this, what I'm trying to say now, even though we know here, the mean here is not the same as the one here, it's not the same as the one here. The difference here is not much pronounced. Even though difference exists, it's not significant. That's what we mean. Maybe the difference here could be attributed to chance. But looking at this guy now, the difference is very much pronounced. This is not the one that we can attribute to chance. Okay, this is a genuine difference. This difference here is very much pronounced, and the difference here is significant. That's what I mean. Okay, so the bus plot is also giving, it's passing across information. Okay, now I want you to pay attention to this, because in the analysis of variance, like I said, we actually measure variability. And measuring variability, that's why it is called analysis of variance. But you know what? Because there are two types of variability that we actually going to be focusing on in one way analysis of variance. Okay, you know what? We actually have a formula, okay, for us to be able to figure out, okay, the variability between groups and the variability within. Okay, now what I want to explain now is actually the variability between groups. Don't forget the other time we're talking about variability between groups. It means we have calculated the mean, sample mean from each group, and we basically want to know how they differ from one another. That's exactly what we mean. Now, because of that, we're actually going to be focusing on what I call sum of square deviations for group. Okay, the sum of square deviation for group now. Okay, what does that mean? It means take a look at this guy now. This is the sample mean that we compute from each group. If we have 3 groups, we're basically going to have this guy here, y bar 1, y bar 2, y bar 3. Okay, now we actually want to know how this differs. Do you know the only way to know how it differs? We basically need the overall sample mean. Okay, the overall sample mean is when I pull all the data together and I find the mean. And what I'm basically going to be doing, I'm actually going to be subtracting each of these from the overall sample mean, and I'm going to square that. Then I'm going to be multiplying each by the number of participants in each group. That is the meaning of this formula here. That's what we call the sum of squared deviations for group, denoted by SSG. Take a look at that. Okay, now when I have SSG, then the next thing I'm actually going to do is to divide it by the degree of freedom. The degree of freedom for group is going to be it's going to be G minus 1. G is the numbers of groups. If you have 3 groups, it's going to be 3 minus 1. And that is what you're going to use to divide the SSG. When you divide the SSG with that, you have MSG. And that MSG is actually a measure of how much means vary from group to group. Is there any question on that? I want to welcome question. Is there any question on that? Okay, if you're still hearing me, I need you to confirm that because of network. I said everyone's still hearing me.
Yep.
Thank you so much. Thank you for confirming that. Now, right now, I just explained the variability between group. Okay, because in analysis of variance, we basically need to compute that. Okay, that's why I'm actually walking you through the variance, mathematics behind the computing the variance now. Now, the next variability is going to be within. We just talked about between. We now want to talk about within group now. And that is what we actually call the sum of square deviation for error. Okay, the sum of square deviation for error. This is more or less like we are trying to, itemize, or we're trying to quantify what is the role or what is the contribution of chance. Okay, the SSE is more or less like getting the contribution of chance. You get what I mean? Okay, getting the contribution of chance. Okay, now when you take a look at this guy now, okay, we actually need the variance from each group. Okay, from each group, X1, X2, in case of 3 groups, that is, so then we actually, so again, we're going to be, so that's going to be the variance from each group. Then we're going to multiply that variance by the number of participants in each group minus 1. Then we're going to multiply that out and sum that. Then that will give us the SSE. And of course, we need to get the MSE. Then we divide the SSE by N minus G. And don't forget, the N here is the overall sample size. Okay, the big N there, the uppercase N, is overall sample size. And this G here is going to be the numbers of groups. Okay, take a look at that. The MSE is an estimate of the sigma square that we call the population variance for each group. And let me tell you this, the population, one of the assumptions of analysis of variance is that the population for each group should be the same. The population variance for each group should be the same. Okay, that is one of the assumptions of analysis of variance. But right now, we don't have that available, that we are computing that, and the MSE is an estimate of that. Just wanted to take note of that. Okay, now we've gotten that now. Then the next thing now, since we've gotten the variation between and the variation within, then we can actually get the overall variability. And getting the overall variability, that is what we call the sum of square total, SST. And in the sum of square total, we basically going to add the sum of square between to the sum of square within. Okay. So if you've gotten that before, we've gotten there before, we can just add that together. But if you have not gotten that, we can also have a formula to figure that out. Okay, we're also going to have a formula to figure that out, which is this guy here, which means I'm actually going to be subtracting the overall sample mean from each of the data point. Okay, exactly what I'm actually going to be doing. Okay, so take a look at that. Now, the moment I have all of that, I'm actually set, okay, to the ANOVA F-test statistic. The ANOVA F-test statistic is basically the ratio, okay, is the ratio of the MSG to the MSE. Okay, you remember that I've walked you through how you can actually call, how you can compute that manually, because the F statistic is just going to be the ratio of the variability between groups to the variability within groups. Okay, that will be the F statistic, okay, for testing the null hypothesis. Okay, so the next on the line is basically we're actually going to set up our ANOVA table. Okay, in the setting of the ANOVA table, G represent the numbers of groups. We're actually going to have the source of variation. Okay, in the source of, the analysis of variance enable us to partition the source of variation into various components. Look at that. Look at, these are the components of the sources of variation. What we're trying to say, the source of variation can be broken down into variation between group, the variation within group, and of course, adding the variation between group to the variation within group together, you're basically going to get the total variation. And of course, we're going to have in the second column, there's going to be degree of freedom. And the degree of freedom, of course, G minus 1 is going to be the degree of freedom for groups. If you have 3 groups, it's going to be 3 minus 1. And this is the degree of freedom for error, which is just going to be the big N, the uppercase N here is the overall sample size minus the numbers of groups. And of course, the degree of freedom for total is actually the overall sample size minus 1. Take a look at that. And the SSG is basically the sum of square variation between group, the SSA, the sum of square variation within group, and the SST, the total sum of square variation. And of course, you know, the other time I show you that this guy here is when you do this divided by this. To get this guy, it is this divided by this. And to get this guy, it is this divided by this. So the moment one is wrong, every other thing is going to be wrong. You got to be careful with the way you set up the analysis of variance table. Okay, now we have assumptions for conducting analysis of variance tests, just like in the t-test that we did the other time. Of course, I walk you through the assumptions under which the test was appropriate. And right now, for the analysis of variance tests, of course, we have assumptions. The assumption number one is, you know, the group, you know, we should have independent random sample from the number from the groups. That is the sample you're actually going to take from the group have to be independent. Then we have assumptions of normality. Each population must have a normal distribution with unknown mean. You know, unknown mean is like unknown population mean. We don't know, we don't have the idea of the mean. Okay, each population has to be normal. And of course, each population must have equal variance or equal standard deviation. So these are the assumptions. Okay. Now, it has been proved that the F test that we're actually going to use, that we call ANOVA test, is robust to departure from normality and equal variance. Okay, so you don't need to be scared about that. Okay, and of course, graphical methods, you know, like histogram or box plot, can actually be used to check the assumptions of normality and equal variance. Okay, now, do you know what I'm trying to show you now? I'm trying to show you the 5-step procedure if you want to conduct analysis of variance tests. You remember what we did in this class last week when we were conducting the hypothesis test. We follow 5 steps. Why? Even under the analysis of variance, we also follow 5 steps. So take a look at the step. You know, in the step, you're basically going to show us your hypothesis formulation, where you're going to specify your known and the alternative. Then you're going to show the test statistic. You know, when you take a look at the test statistic here, actually follow normal distribution. Okay, the normal distribution with 2 degrees of freedom. The first degree of freedom is basically G minus 1, and the second degree of freedom is A minus G. Okay, I wanted to take note of that. Okay, and of course, we can actually find a p-value associated with that. We have a coding now, okay, which my TA is going to walk you through that this week in the lab. Okay, and of course, it's the same decision that we take all the time, where we compare the p-value with the level of significance. When the p-value is less than the level of significance, we're basically going to reject the known hypothesis. And when the p-value is greater or equal to that, we're actually going to fail to reject H known. Okay, so it's basically going to, you know, that would be the same decision we take all the time. I'm going to say that again. When p-value is less than alpha, we reject the H naught. But it is greater or equal to, we fail to reject that. Okay, so this is just to show you the distribution, you know, of the non-hypothesis. They have distribution. Okay, so this is just to show you that. Okay, this is a property of the F distribution. It is non-negative, it is right-skewed. Look at that. This is right-skewed. This is not normally distributed. Okay, this skewed to the right. Okay, and mean is approximately 1. Okay, and the mode is approximately 1. Okay, and with the exact value for that, you know, for the degree of freedom greater than 2, and so on like that. Okay, let me tell you this, you know, when you conduct your F statistic and you basically want to figure out the p-value, right? You know, I told you we have a coding now to figure out this p-value, right? You know, following, you know, the value you got here, how do we get a p-value associated with that? We got a coding now. Take a look at this. Now, when you take a look at this, let's say, for instance, my F statistic value is 3.493. I'm just assuming. I'm assuming that maybe after computing this, right? Maybe in the ANOVA table, maybe after getting all the way here. Okay, how do I get a p-value associated with that? Okay, now to get a p-value associated with that using the R code, if I'm assuming that the F statistic value that I got is this guy, then I also need a degree of freedom. Now I'm going to go back, the DF1 equal to 2 here. Maybe I'm talking about the degree of freedom for the group, for situation where we have 3 groups. Okay, so all the time, I'm actually going to use the degree of freedom for group and the degree of freedom for error. Okay, and that was why here you actually seeing DF equal to 2, equal to 20 here. It means the 20 is basically going to be the degree of freedom for error, and why this one is going to be the degree of freedom for group. And of course, you're actually going to have a lower equal to F, and that is going to return the p-value, okay, that you're actually going to use in taking decision. Now take a look at this now. When the test statistic value is 7.42 and you have the different degree of freedom, the p-value you're actually going to have will be different from that. So take note of that. Okay, is there any question before I move on? Is there any question? I need everyone to confirm again if you are still hearing me clearly. Is everyone still hearing me clearly?
Yes.
Thank you so much. Thank you for confirming that. Okay, now I want to go back into the example that I cited the other time on where we actually want to compare anorexia treatment method. Don't forget we got the 3 types of the method, the therapy that we talk about. One is cognitive, the other one is family therapy, and the other one is actually, in the control group. And what we're looking for is just the change, the weight change. Okay, and of course, the weight change is just going to be after following the treatment. The weight change is going to be the difference between the post-treatment and the pre-treatment. Before they go into this, the experiment, they actually measure the weight of the participant, and after the treatment, they also have a measurement of the weight, and of course, then we calculate the weight change by subtracting the pre-treatment weight from the post-treatment weight. Okay, now the question now is, we want to conduct analysis of variance tests, where we actually want to compare. Somebody said, could you give an example where we will use ANOVA? I joined a couple of minutes late. Oh, okay. Where we use ANOVA is when you are comparing means in more than 2 groups. I'm going to say that again. When you are comparing means in more than 2 groups. I don't know if I've answered the question, the person that chat with me, the person that joined late. Okay, thank you too. Okay, now we want to conduct analysis of variance now by filling in ANOVA table and use it to perform the test for equal mean weight gain among 3 anorexia treatment at the 0.05 level. Okay, I wanted to take note. You see, if you use all the formula that I showed you the other time, you're actually going to end up here. Now, let me show you the table again. Okay, this is the table. Because we got 3 groups, it's going to be 3 minus 1. This is going to be 2. Okay, so this is going to be the total number of sample or to the SSG I showed you the other time, how we can compute that using the formula here for the SSE, how you can compute that using the formula here. And of course, at the end of the day, we're actually going to fill up the table. Okay, we fill up the table now. We have the S statistic to be, let me just tell you, the moment you have this guy, you have this guy, maybe you've been given this. So this is going to be this divided by this, you have that, this divided by this, you have that. And if I want to get this guy, it is this divided by this. And of course, the 71 here is like adding this to this, and this guy here is like adding this to that. Now, the next thing you're going to be looking for, how do you get a p-value associated with 5.42? Now we're going to go back to the procedure. Again, look at the procedure now. We've stated our test statistic, and of course, the p-value associated with that, we can compute that. You know, if you follow what I show you here on how to compute the p-value using R, you just need to specify your test statistic and your degree of freedom, and your p-value will be automatically computed. And of course, in the end, the conclusion that we actually take here is that we reject the null hypothesis and conclude that the mean gain is different. Is different in the sense that because of the fact that the p-value is less than, you know, the level of significance. That was why we actually rejected that. Okay. Now how do we do this in R? Okay, how do we do, like, if I don't want to go through the rigorous way of setting up the table, if I don't want to do that manually, how do I actually do that now? What I need to first do, I need to import my data set into R. When I import my data set into R, and I actually take a look at this now, that's a therapy, right? This is the change, the difference in the weight, okay, before and after the therapy. Then I'm just going to write AOV. Then the summary of AOV will return the whole of this. In fact, the arrow code will automatically return the p-value that we're looking for. Okay, look at that. Okay, this is how the arrow is going to compute that. Like I said, my TA is going to walk you through how to figure this out in the lab this week. Okay, now you can see the p-value here is actually very, very small compared to 0.05 level of significance, and we basically reject the null hypothesis because the p-value is less than 0.05. Now, what is next? So what is next is going to be, well, after rejecting the null hypothesis and analysis of variance, can we do a follow-up to be able to know where the difference lies? We basically want to know where the difference lies. Don't forget, we're comparing three groups. The analysis of variance is only going to tell us different exists, but the analysis of variance cannot tell us where the difference lies. I'm going to say that again. The analysis of variance is only going to tell us whether difference exists or not between, in more than two groups, when you're comparing more than two groups. But the analysis of variance will not tell you where the difference lies. But how do we analyze where the difference lies if we have rejected the null hypothesis in the analysis of variance? That is what we're going to do next on Wednesday. Is there any question for me today? Is there any question?
No.
Okay, I want to use this opportunity to actually thank everyone who have attended my lecture today. Like, I'm going to once again apologize. It was, what happened initially to me today with my car due to weather, but I'm fine now. Everything is resolved now. I'm actually we're going to return to in-person teaching on Wednesday. Until Wednesday, make sure you stay safe. On the road is very icy. Okay. Until Wednesday, okay. Make sure you stay safe and have a lovely day. Bye for now, everyone.
Thank you.
You're welcome.
Thank you.
You're welcome.
Thank you.
You're welcome. And this is being recorded. I'm going to, publish that later. Okay. You can check the canvas for the recording. Okay. Bye.